So let's look at another problem here. So we have a Carnot engine 1 which works between temperature reservoirs A and B, and another engine 2 which works between reservoirs B and C. Okay, let's maybe draw them. So this works between A and B. And the other works between B and C. Okay, so that's something like this. Both of these are reversible engines. The temperatures of A, B and C are given. This is 850 Kelvin, 450 Kelvin and 250 Kelvin. In any cycle, heat rejected by Carnot engine 1 to reservoir B is used by Carnot engine 2. Okay, this is engine 1, this is engine 2. So what we are given is any heat rejected here is used over here. So for one cycle, Carnot engine 1 absorbs 150 megajoules of heat from reservoir A. So what we have is that QA is 150 megajoules of heat. We are asked to calculate the heat rejected by Carnot engine 2 to reservoir C. So essentially QC is what we are asked to find out. Of course, these are Carnot engines, so they would give out work. Of say W1 and W2. So this is what is given. So these are Carnot engines, so therefore they are reversible engines. So because they are reversible engines, we can write some expressions. So we know that QA by QB1 should be equal to the ratio of the temperatures, which is 850 by 450. Similarly, for this reversible engine, we see that QB 2, which is equal to QB1. So I'll just write it as QB. I'm not taking the signs, I'm taking positive values here. So I know that for this engine, this is heat going out, it's negative. For this engine, it is heat coming in, it's positive. But numerically, the values are equal. So I'll just call it as QB by QC. I'm taking positive values for all of these. Should be equal to the ratio of these temperatures, 450 by 250. So that's also something I have. And I know QA, so I can find out QB from here. So that's QA, which is 150 megajoules into 450 Kelvin divided by 850 Kelvin. So the answer will be in megajoules. So that's about 79.5 or 79.4 megajoule is QB, which is coming in over here. So now I know the value of QB, I want QC. QC is QB into 250 by 450. Which is about 44.1 megajoule. Yeah, so that's the value we are looking for. So this is the value. Of course, we could also find out work done by each engine and so on, but it's not asked for in this problem. We have here another problem. It says the refrigerator has a COP of 2.5 and a power input of 500 watts. Okay, so let's draw a refrigerator as a schematic. So it's trying to remove heat from this, which is what we want to cool. and sending it out to the atmosphere. The COP is given as 2.5. In the refrigerator we need to give work. The amount of power input is given as 500 watts. We call that as W naught usually. So that is 500 watts. It has to cool 7 big watermelons. This is a pretty big refrigerator. So it has 7 watermelons inside, which are at 25 degrees initially to 8 degrees centigrade. Okay. So this is, we see a transient problem. We have substances which are at initially 25 degrees centigrade, which is 298 Kelvin, which is the initial temperature of the watermelons, and we want to cool this to 8 degrees centigrade. So we add 273 to this. So we have about 281 Kelvin. The weight of each watermelon is 10 kg. And there are 7 watermelons. So the total mass is 7 times this, which is 70 kg. This must be a pretty big refrigerator indeed. So watermelon can be treated as water with a specific heat of 4.2 kilojoule per kg. So watermelons are, I think, more than 90% water, about 93% if I remember some trivia correctly. So it says we can treat these watermelons as water, and the value of specific heat is 4.2 kilojoule per kg Kelvin. We know that for liquids and solids, we take it as either Cp or Cv because there is no significant difference between them. It says how long will it take for the refrigerator to cool them to the required temperature. Okay. So we want to know the time it will take to cool this. So we are going to make some assumptions here. First is we are putting the watermelons inside this. We are going to assume that the temperature of this refrigerator is the temperature of the watermelons. So we are putting the watermelons and then starting to cool it. The refrigerator is already not cold. Secondly, we are going to assume that we are cooling only the watermelons and not the insides of the refrigerator, or there is nothing else in the refrigerator and so on. So if this was a reversible refrigerator, then it would run on a Carnot cycle. But anyway, the COP is given. So let us see what is the COP here. So we call this as QH, QL, and we call this as W. So what we have is that the COP for the refrigerator is what we want, which is essentially this heat removed, divided by what we need to give, which is essentially the work, and this is given as 2.5. So that is something we have. So the QL is what we are removing from this over here. In this case, we are trying to cool these watermelons. So the heat which we need to remove is given as m into C into T final minus T initial. So that is 70 into specific heat is 4.2 kilojoule per kg, is 70 kg. This is kilojoule per kg, this is kg, sorry, this is kilojoule per kg Kelvin, this is kg, and this is essentially 298 minus 281 or 25 minus 8. We are only looking for a difference. So we can calculate this. This comes out to be 4998 kilojoule. So we need to remove this much amount of heat in order to cool this. So given that the COP is 2.5, the amount of work we would need to do is essentially this divided by COP. which is about so many kilojoules. So W dot, which is power, is essentially work divided by time. This is the work, this is the power. We need to know the time. Time is W divided by W dot, which is essentially, this is W. W dot is 500, so which is about 3.99 into 10 power 3 seconds. This is in kilojoules, this is in watts, so this is into 10 power 3 joules. This is a watt, which is a joule per second. So I get this time. So that's 3.99 10 power 3. So I can also divide it by 3600 and I get the time as about 1.1 hours, which is the time I need to cool this. So that's the first part of the question. Second part is, in reality, will the time taken by the refrigerator be greater or smaller than the time you calculated? So in reality, what we have is that if this fridge was initially at room temperature and we switched it on, we would cool not only the watermelons but also the air around the watermelons and also the inside surfaces of the fridge. That is something. Plus, in reality, we are going to have a lot of other losses. So we are going to have losses through the walls, because heat is going to enter through the walls of the fridge, because the fridge is not completely insulated and so on. So therefore, in reality, our time is almost always likely to be higher than this. Of course, if the fridge was already cold and you put the watermelons inside, then it could be either way. But if the fridge was off, we've got a new fridge, we bought it and we want to inaugurate it by putting watermelons inside, it's going to take a much longer time than this. So we'll stop here with this. Thank you.